this is not a this problem has a lot of layers. Okay? It's not impossible to solve, but first time when you look at it, it's pretty overwhelming. So the thing is we have to, I'm going to start on a new page with this diagram over here. So we need to locate, based on this figure over here, we need to locate where failure will occur. Okay, this is really critical. Okay, so we are going to, and what do I mean by that? Okay, so we are going to have this as our x, and I'm going to call this our y, and I'm going to call this direction as our z for this case. Okay, and not only we have to determine where failure will occur. Okay, we also have to find out tau max, which equation to apply. Both are Tresca, but once user stress max divided by 2, this occur when stress mean is equal to what? It's 0. Okay. On the other condition, stress mean is not equal to what? 0. Okay. So you cannot just look at the formula, okay, I'm going to use stress max divided by 2. No. Okay, you have to be very sure, okay, when to apply what. So from here, you need to locate where failure will occur. Okay, we know failure will occur on this phase. That's the only thing we know. But exactly where will it start? Okay, I repeat again, where will it start? That is the critical part. Okay, where will it start? Okay, so if we were to look at we will look at our loading, we will have px, right? And the px will be minus 2,500 pounds. And this px we can apply, we can use to determine with stress x is equal to px over a. Because if we were to draw, okay, like what I taught you guys before, we were to draw our neutral axis where the element will be placed. This is the neutral axis. This is the axis of interest. Okay. Right. So now the problem with this question, I'll write more stuff first. Okay. Let's look at all our loads first. Okay. We also have a torque in the x direction acting at 2,300, and I'm going to multiply by 12 to change it to pound inch. Okay, so 2300 times 12 is equal to 27600, and now this becomes pound inch. It's important to change to pound inch because our stresses is in pounds per square inch. And then we know that we have a moment about z, right? The moment about z given to us is at 1,500. Okay, 1500. Again, multiply by 12. Is equal to 18,000 pound inch. Okay. So now I'm going to sketch. So before I sketch anything, we know that this structure will be going through stress in the x direction. This will be equal to px minus px over a. And then we have plus minus mz over izz multiplied by y plus minus my over iyy multiplied by z. And we can cancel out this term because this is equal to what? This is equal to 0. Okay. And then the next one, we know that we have a shear, right? And the shear is equal to what? Tx multiplied by c divided by j. Okay. So there are two formulas that we are going to use. Okay. And our highlight over here, right, where c is the c is the radius of the shaft. J is equal to 2I, okay, and J correspond to our polar second moment of area, okay, and I is our second moment of area. Okay. So we know to determine our stresses, we have to use these two equations. Okay. Now, where is the location where maximum stress will occur? Okay. So now what I would like to do now is I like to draw from the view. We are going to view this in the Y. This is Y. This is Z. This is our rotational X. Okay. And then what we're going to do is this is our shaft now. Okay. This is our shaft. And I'm going to draw a crosshair. Okay. And over here, okay, I'm going to position different elements. Okay, so I'm going to have my element I, element J, element K, and element L. Okay, so we have element I, J, K, and element L. Okay, so what I'm trying to do is I'm trying to locate which element has the what? Highest stress. I repeat again, I'm trying to locate which element has the highest stress. You know, a lot of problems that we have, a lot of problems like the one that we solve, not solve, but the example we have over here, right? It tell you, okay, calculate the stresses for element A and determine the stresses for element what? B. Okay, really straightforward. So you just apply the formula and then you just go for it. Okay. For this case, they did not tell us where are the elements. We only know this is the failure phase, or the phase where failure will occur. But they did not tell us where is the maximum stress is, or which element has the highest stress. Okay, that's why I tell you, this is the real engineering problem. How I wish there are more problems like this in our engineering degree. Okay, because most of the time what we do is I give you a question, okay, telling you exactly what to do. For this case, analysis. Okay, you have to analyze where failure will occur. Okay, and you have to be precise. It's not a guessing game. Okay, This is not a guessing game at all. Okay. So now we are going to draw a table, and I'm going to now draw a table. So this is element. Okay. I, J, K, and L. Okay. And if we look at the formula, if we look at the formula minus px over a, right, which is the axial loading, right? So if you look at the axial loading, element I will see minus px over a. Element J will see minus px over a. Element K will see minus px over a. Element L will also see minus px over a. So while looking at the axial load, we don't know. We can't tell. Then next we come look at the bending moment. So we have mz over izz multiplied by y. Okay. And based on how the arrow is orientated, right? So we know that this is our moment, right? We know that this is our moment in the z direction, right? Moment in the z direction. And we know over here, this is compression. We know over here, this is what? Tensile. Using what we learned 3 weeks ago. Okay. So from here, right, we look at this formula now, right? So we know element I is in what? Element I is in compression. Okay, so we know that this is minus mz over izz multiplied by y. Element J is on the neutral axis. Neutral axis, the term used correctly, is equal to what? It's 0. Element K is in tensile, so this is positive. And then element L is on the neutral axis, is equal to what? 0. And then finally, we have Tx over C, or Txc over J. Okay. And all of them, C is the radius. Okay. Our radius is equal to C. So all of them as Txc over J. This one also Txc over J. This is also Txc over J. And this is also Txc over J. So from here, we are able to locate the what? We are able to locate the position of maximum what? Maximum stress. Which element will go to the maximum stress? And the answer is element I. Element I will see the maximum stress is purely because what we have over here is we have compression due to axial load, and we have compression due to what? Bending moment. This is where the analysis comes. Okay, as I said, how I wish we can have more problems doing analysis like this, but unfortunately, that's not the case. This is a rare situation. Okay, a very interesting but real engineering problem. Okay, this is what you get in this is what you exactly will get in industry, or as an engineer, as a failure analysis engineer, as a design engineer. Okay, they will not tell you this is the element. No. Okay, you have to identify. This is where the analysis come up. This is where you earn a lot of money. Okay, unfortunately, right. So once we know that we have our element I. Okay, I'm going to use this diagram again. So the next thing we are going to state that element I right will be under the highest stress. Okay, right, will be under higher stress. Okay, and we don't need to spec. I mean, maybe you can say it's highest normal stress. Okay, because the shear stress are all equal. So now next thing we're going to do is we are going to draw the element. Okay, exactly like what we see down here. So we know that this is X.